Hello and welcome to Lecture 1 of Electric Fields in Phys 1204. I will just warn you before I start this lecture that the idea of a field is an inherently mathematical idea, and so this lecture will be somewhat more mathematical than the introductory lectures of most units. To start thinking about the idea of a field, let's think about a hypothetical question, which you may have heard before. It concerns an experiment which I sincerely hope nobody ever carries out. Suppose that somehow we could just magically make the sun go poof and disappear. The question is, how long would it take for us to notice that the sun was gone? The obvious answer that we would notice right away is in fact wrong, and you have to think about how we know the sun is there. The sun is interacting with us, and the main way we notice that the sun is interacting with us is that light arrives at the Earth. The sun, through shining, has filled all of space around it with light, and that light is streaming outward from the sun. So we've just made the sun go poof, and so there's this empty hole where the sun used to be, but there's presumably all of this light still filling space, and it's all moving outward, which means the hole with no light expands outward, and the point at which we notice that the sun is gone is when the edge of that hole with no light in it reaches us. It turns out that that would take about 8.5 minutes. This is relevant to thinking about interactions between charged particles. Suppose we have two particles, Q1 and Q2. Then Q1 will exert a force on Q2, which we believe is given by Coulomb's law. But suppose we wiggle Q1 back and forth. The force that it exerts on Q1 depends on the distance r, and if we wiggle Q1 back and forth, that distance changes. That ought to cause the electric force to change, and in fact it does, except that experimentally we always see that it doesn't change it immediately. There's a delay. Apparently the disturbance to Q1 takes some time to travel to Q2. So the picture we have, again, like the light filling all of space due to the sun, is that Q1 has somehow filled all of space around it with some influence. It's changed space around it somehow. And when we wiggle it back and forth, a disturbance in that changed space propagates outward until it reaches Q2, at which point we observe a disturbance to Q2. This changed space around Q1 is what we refer to as a field, and this is a model for the interactions between charges. The field I'm describing is what we would call an interaction field that governs the interaction between particles. The more general mathematical meaning of field is useful because an interaction field is a more general mathematical field. So a field is just a function which assigns a value to every location in space. That may seem abstract, but you've actually seen them regularly. For example, a temperature map assigns a value of temperature to every location. So it is an example of a field in the mathematical sense. Notice that temperature is a scalar, and so this is a scalar field. However, what we'll be more interested in are vector fields, where every location has a vector assigned to it. Again, that may seem a little abstract, but again, you've probably seen things like it. For example, a wind map that shows the direction and speed of the wind at all locations is an example of a vector field. Notice you can't actually draw a vector at every point on the map. If you did, the whole map would just be black, and that wouldn't be very useful. So you have to draw a representative set of vectors. While our goal is to learn about electric field, I'm going to start off with the gravitational field. This is to give you a better idea of what an interaction field is in general. And I'm starting with the gravitational field because it's a little bit simpler than an electric field, and also you're going to see that you've already seen it, though we didn't call it the gravitational field at the time. So let's think about the interaction between the Earth and the Moon. We think of the Earth as producing a gravitational field that fills space around it. Wherever the moon is, the gravitational force on it is a result of the field at its location. Similarly, the moon produces a gravitational field around it, and the force that it exerts on the Earth is thought of as being a result of the moon's field at the location of the Earth. Similarly, we could think about you standing somewhere on the Earth. Then the force exerted on you by the Earth is due to the Earth's field at your location. There's also a much smaller gravitational force exerted on you by the moon, so small you never notice it, and it is due to the value of the moon's field at your location. Note that we say then that at your location the Earth's field is much stronger than the moon's field, because the Earth is exerting a much stronger force on you. I want to head off a source of confusion, though, right away. Fields exert forces, but fields are not the same as forces, and in particular, they aren't measured in the same units as forces. Let's say we're talking about some location A, near the Earth, near the surface of the Earth. Then we can place some mass, we call it m1, at location A, and the Earth will exert a gravitational force on it. Now I could replace m1 with some, say, smaller m2. Well, m2 is going to experience a smaller force due to the Earth. However, we believe that there is a gravitational field vector at the location A. Well, in fact, there's a gravitational field vector at every location, but at the moment we're interested in its value at location A. The fact that the forces on M1 and M2 are different does not mean that the field is different depending on which mass we use to measure the field. The field has to be a property only of the Earth and of the location where we measure its field. So the value of a field in general, or an interaction field, depends only on the source of the interaction field, which in this case is the Earth, and the location where we're measuring it. It never depends on what we use to measure it. This is the key idea of an interaction field. The field at any location is produced by some source. So in the case of a gravitational field, it's produced by a source mass. The field can be felt by a probe, in the sense that any probe that we place at a location will feel a force which is exerted by the field. So the fact that M1 is feeling a downward gravitational force when it's at A tells us that there's a downward gravitational field vector at A. But the value of the field itself must be independent of any property of the probe that we use to measure it. That immediately tells us how to determine a gravitational field. If you just look at the expression for the gravitational force on M1, then the part that depends on the probe is the part we have to remove to get the field. Well, the only part of the expression that depends on the probe is M1, and so if we remove that, we'll be left with the gravitational field vector. That's easy. Dropping the M1 out, we get a gravitational field vector that is just G down. Well, how do we drop it mathematically? We have to divide it out. So this is our prescription for determining a gravitational field vector. We put a probe mass at a location and measure the gravitational force on it. If we then divide that gravitational force by the probe mass, we'll be left with the gravitational field. Let's summarize these properties of the gravitational field, because all of these properties will hold for an electrical field as well. It exists at all points in space, and it depends on location. So while near the Earth's surface, it's G down, if you go farther away from the Earth, its magnitude decreases. It depends on the source. So, for example, if you measure the gravitational field due to the moon, you will find that it's weaker. and it's independent of the probe used to measure it. That's because the gravitational force is proportional to the mass of the probe you use, but you then divide that out, and so you get an answer that's independent of the probe. All of this will apply to the electrical field as well. The specific expression for how you determine it won't, but the idea that we used to get that expression, which is that the field has to be independent of the probe used to measure it, does apply to electric fields. So now let's shift from gravitational fields to what we're actually interested in, which is electric fields, and we'll use the same idea. The field is going to be independent of the probe used to measure it. So let's think about some charged particle Q, and we think that space is filled with some electric field around Q. And let's think about a location A. Of course, this field exists everywhere, but let's focus on a single location A. And we'll think of putting a probe particle there with some charge Q1 and some inertia M1. Then if we replace that probe 1 with a probe 2, which has a larger charge, say, and it doesn't have to have a larger inertia, but definitely a different inertia, we will use this to think about how we obtain an electric field. Note that we are swapping between two probe particles to probe the field due to a source particle. And the answer will depend on the source particle, but will not depend on the probe particle. You are going to reason out how we get the electric field, but the reasoning shouldn't be too hard if you just apply the idea we've seen. So to get a gravitational field, we saw that we divided the gravitational force by the mass of the probe particle, and we got a result that was independent of the probe particle used. So first, think about whether dividing the electric force by the mass of the probe particle will give something that's independent of the probe particle, and if not, how can we get a quantity that is independent of the probe particle? I'll tell you that you know how to calculate the force that Q exerts on each of these probe particles. It's Coulomb's law. And so all you have to do is look at Coulomb's law and see what part we have to remove to get an expression that's independent of the probe particle.